Guys, here we actually have a real example with real numbers, and we're going to walk through on how to solve the algebra and the math. So up at the top, an internal standard is a known concentration of a substance that is present in every sample that's analyzed. Internal standards can be used with either the calibration curve or standard addition methods, although the former is probably more common. The purpose of the internal standard is to behave similarly to the analyte, but to provide a signal that can be distinguished from that of the analyte. Ideally, any factor that affects the analyte signal will also affect the signal of the internal standard to the same degree. Thus, the ratio of the two signals will exhibit less variability than the analyte signal. Internal standards are often used in chromatography, mass spectroscopy, and atomic emission spectroscopy. They can also be used to correct for variability due to analyte loss in sample storage and treatment. So the example problem says, in the analysis of sodium metals by flame atomic emission spectroscopy, lithium may be used as an internal standard. They're similar. Look at them on the periodic chart, right? Look at their locations. Using the data below, calculate the concentration of sodium in the sample. Compare the precision of the result from the internal standard method with that achieved with just a calibration curve. So pretend that the lithium were ignored. It didn't even get ran. Plot that calibration curve and compare the two. So here's the data that they're giving us. 0.2, 0.5, 2, and 5 part per million sodiums. And it looks like a 500 part per million lithium is all the way down. And then we have a sample at the very bottom. And the sample is an unknown concentration. We don't know how much sodium is there. But, lithium was the internal standard. So I've put the lithium in the sample, and I know how much lithium I put in there. So 500 ppm is what we've got. So now I need to figure out, well, what do I do with the numbers? After I ran them, these are the signals that I've achieved. 0.22, 0.53, 2.35, and 0.88. But I'm also including lithium, 48, 47, 51, 46, 48. Remember, internal standards, the areas and the signals, well, theoretically, they should be the exact same number. But I know that there's variability in all of the analysis parts of the preparation, of the instrument, of the injection, of how it sees its sample. I know it's going to happen everywhere. So the numbers are going to be close, but they're not going to be identical. And that's what I'm seeing, right? 48, 47, 51, 46, 48. They're all in the ballpark figure. Reasonable. So I need to go to Excel and I need to plot a calibration curve, and it tells me I also need to plot a calibration curve using the internal standard, and I need to compare those two things together. So let me open up Excel. So here we go. So the first part of the question said, just pretend like lithium wasn't ran. Just pretend like this is a normal calibration that you would have done in any old day leading up to this lecture series, because you didn't know what an internal standard was at that point. So I'm just going to pretend like lithium's not present. And I have a 0.2 and a 0.5 and a 2 and a 5. And then I have a signal associated with each one of those. So a 0.2 part per million sodium gave me a 0.22 absorbance, 0.53, 2.3, and a 5. And it told me to plot them. So I'm going to go in and I'm going to do what I normally have always done. I go into a scatter plot mode. Here is my graph. Let me shrink that down a little bit so I can put it on the screen. And I'm going to click a data point. I'm going to add a trend line. And I'm going to choose linear and choose the equation and the r-squared value. All right, so there we go. So the first part of this problem is now completed. It wanted me to treat this like any old calibration step, and this is what I did. I plotted the concentration on the x-axis, and I plotted the signal on the y-axis. I did a linear regression curve, and looking at this, it looks pretty good. 0.9958. Right? I did a really good job preparing the standards if these are the signals that I received from them. It looks like standard number 3 is a little bit high. And we would have originally looked at this and we would have said, you know what, you probably added a little bit more than what you needed to in standard number 3. But, you know, overall you did a really good job. So we'll pat you on the back and away that you go. But now you need to keep in mind that the instrumentation can cause you problems, right? So I'm going to scroll down and I'm going to do this again, but this time we're going to include the actual lithium internal standard. So how do we do that? Well, I do it the same as before. I plot my concentration of the sodium. 0.2, 0.5, 2, and 5. All right, well, the signal from my sodium is 0.22, 0.53, 2.3, and 5. But I also have a lithium standard as well at a 48, a 47, a 51, and a 46. Notice I've not done anything with my sample yet. Okay. To handle an internal standard, we said that this should be a constant number, and constant numbers typically go on a denominator when we can allow them to. So what I need to do is I need to calculate a ratio here. So I'm going to hit equal, and we need to take the area from the sodium divided by the area from the internal standard, and I hit enter. And this gives me a ratio now. And I'm going to do that all the way down. And there's my ratios. 004, 01, 04, and 108. Keep in mind that as the concentration increased, the ratios increase, right? That's the reason that we put the constant value, the internal standard, on the bottom. This number is not going to change that much, and because of that, my ratios are not going to deviate greatly from the signal relationship. So I've plotted, or I've keyed in the area from my analyte, sodium, which is what I want to measure. I've put in the lithium, and I've done a ratio between the two. Remember what we said? We said, hey, number 3 looks like it's a little wonky. But look down here. Out of all of the internal standards, we said these numbers should be constant all the way through, right? This one was the greatest, number 3. So maybe it wasn't me that messed up the standard prep. Maybe the machine just accidentally went through and injected a little bit too much on standard number 3, and the internal standard tattled on it. It let me know what happened in that analysis. All right, so I've plotted now the concentration as well as the ratio. I normally do not like to split the cells. I just get a little weirded out about it, so I'm going to type in the concentrations again, and this time we're going to plot another calibration curve. We're going to do the concentration of sodium on the x-axis and the ratio on the y-axis. I'm going to go in and I'm going to plot a calibration curve, and there it is. Looks pretty good. And I'm going to add a trend line, r squared, and the equation. And there we go. Now, I want to compare these two graphs. This one was done without the internal standard. This one was done with the internal standard. First, the equations are not going to be the same. This used a raw signal from the data sheet. This used a ratio from the data sheet. So the y equals mx plus b, you cannot compare those with each other, right? They should not be the same. They should not be identical. They're telling you different stories because we're plotting different numbers. Bottom line, that's what's happening, right? The x values are the same, but the y values are drastically different. 0.22, 0.53, 2.3, and 5, and 004, 011, 045, and 108. They're not going to give you the same y equals mx plus b. What we want to look for is our R squared value. Our R squared was always an idea of linearity. So how is the concentration related to the signal? Is it in a linear fashion? 9958, that's pretty good. We would let you slide by with that, and we would, again, pat you on the back and tell you good job. But look what happens when I bring in my internal standard. My internal standard takes care of all of the variations that might happen throughout the analysis, especially within the equipment. And that R squared value improved. It went to 0.9998. I can't really ask for any better than that. So out of these two calibration curves, the second one is going to be much better. And the reason is because in that second one, my R squared is better than what it was from the beginning, if I just plotted strictly the absorbance values. Again, the concept is the equipment. How can you rely on the equipment to inject what it's supposed to be injecting? And the internal standards can take care of that for you. All right, now I want to take a look at the samples. The samples look like it had a 0.88 for the sodium and a 48 for the lithium. In a normal calibration curve, what would have happened is that I would have said, well, I don't really know this concentration, so I'm going to keep it as an X. That was a 0.88. So what I would do over here, I would type in Y equals, this is 0.9962, and this is X plus 0.0948, Y equals, X, because I'm solving for the concentration. The Y value is 0.88, right? That was the signal from the sodium, 0.88. That goes in for Y. Subtract 0.0948. And then to solve for X, we would divide by 0.9962. And this is the concentration that I would get for sodium. That nothing changed. What I've just done is the same thing that you have done throughout the entire semester and throughout the entire program. I've taken the signal from a sample, I plugged it into the regression line, and I solved for X. Simple as that. All right, now let's look how to handle that with an internal standard. This is a concentration that I do not know. It's 0.88 is the signal, and 48 came from the lithium internal standard. So notice that Excel automatically knew what I wanted to do with it. It wanted me to take a ratio. I can check that calculation up here at the top in the formula bar. It took B18, which is 0.88, and it divided it by C18, which is 48, and it gave me a ratio number of 0.0183. You treat this just like you've treated the one up above. There's no difference here. Y equals, this is 0.0217, X plus 0.0007, X is equal to, well, I take the ratio now, right? Because the internal standard graph is based on ratios. So I take the ratio of the sample, 0.0183, plug it in for Y, subtract 0.0007, and then divide by 0.0217. And I get 0.8125 part per million sodium. Notice how these two numbers are different. 0.788 and 0.812. They're close, right? They are close. But out of these two versions, the internal standard graph gave me a better linear relationship. Therefore, the internal standard graph is going to be the most preferred graph out of the two. And out of these two answers, the 0.812 is going to be the one that I would want to use and report as a value. If I took the trouble in doing an internal standard, I'm going to take the trouble in solving for that one using my samples and reporting that data, because on the books, as far as the science goes, this is a more solid, a stronger foundation as far as data is concerned. Okay? So that's how we handle an internal standard calculation. You plot your standards just like before, but this time you plot them using the ratios. That's the only difference that you're doing. It's the ratio here. Your sample will have something similar. Therefore, you do the ratio for the sample. Once you plot your Cal curve, once you get your linear regression line, once all of that goes onto the graph, you solve it just like you've always solved calibration curves. There's no difference, except for the fact that you are putting your ratio in for Y instead of the hardcore signal that you're getting for the Y. That is the only difference in the calculation part. I got a 0.812, and you know, this could be the difference between life and death. If this was in the pharmaceutical world, I would want to be really particular on how much is actually present. If this was an environmental lab, I would want to make sure that this is as close as it can get to the true value, because that could mean the difference between calling the EPA and notifying them of a contamination or just letting it slide. You've got to be particular. You've got to be careful, and the machines can lie. And the machines are not dependable every single time. And an internal standard is going to help you with that process.